All right, so this is the second part of the lesson on completing the square and the last lesson in Chapter 3. And again, the focus of Chapter 3 being understanding the connection between graphs of quadratic functions and their equations. This lesson, finishing off completing the square, is mostly looking at a few different applied problems, but I start with one more purely algebraic problem, which is more or less just kind of annoying, not so much as difficult as just it's annoying. But same idea as what we would have covered in the last video. And so again, if I want to write this in vertex form, I need to notice there's a 4. The leading coefficient of x squared is 4. That means I know if I'm thinking about a vertical stretch, this has a vertical stretch by a scale factor of 4 compared to x squared. But more importantly, if I want to complete the square, I need to factor this out from the first two terms pretty much right away. So I'm going to rewrite this as 4, take out a factor of 4 from the first two terms. And what's kind of annoying is that 4 doesn't divide into 28 nicely. What am I talking about? Yes, it does. Never mind. 4 divides into 28 just fine. Take out a factor of 4 from 28, or negative 28, and you get negative 7x. And again, give myself some space, because I want to create a perfect square right here. And that minus 23, I'll just kind of shove off over here. OK, so now to create a perfect square, this is where actually things get a bit annoying. But we saw similar things in last day's lesson at the beginning. Whatever goes here, that negative 7, I need to chop it in half, so negative 7 over 2, and then square it to figure out what goes there. So in this case, I get positive 49 over 4. Like I said, it's not so much difficult, it's just kind of annoying. It's nicer when we have nice whole numbers. That's it, I need to balance this out. And so whatever's going to go right here has to balance out the change I just put in. Yes, I wrote down plus 49 over 4, but that's all being multiplied by 4. And so really, it's 49 divided by 4 times 4. And I don't need a calculator to know that those 4s are going to cancel out. So that's just, I really added 49 to the equation. And so I need to subtract 49 from the equation right here. And now everything's balanced out. OK, now I need to factor what you see is highlighted in blue, that perfect square. And again, I know the factors, well, it has to be a perfect square, so the same factor twice. It's going to be x minus, and it's always, again, as we saw last time, half of that value there. So half of 7, so 7 over 2. So we see there is equivalent to what's above it. And then minus 49 minus 23 is minus 72. And again, that vertical stretch I could see right from the start, but now I can see all the basics of this function. I can see it has a vertex at 7 over 2, or 3.5, and negative 72 on the y. I can see that it's opening up, because my a value is 4. I can see there's a vertical stretch by a scale factor of 4. And again, I can always see all those things once it's written in vertex form. So with that said, though, I have 2 more problems, which will take a little while. And most of these are looking at applications of this, that at some point completing the square will come into play. So as it says here, a sporting goods store sells reusable sports water bottles for $8. At this price, they sell approximately 100 items per week. Research says, a survey of some sort says, they predict that for every $1 they increase the price, they expect to sell 2 fewer water bottles, which makes sense. You raise the price, you expect you're going to sell less, but you make more on each. So it may not be inherently a bad idea to raise the price. Just like lowering the price is not always inherently a good idea. Yes, you may sell more, but you make less money on each. And so model the expected revenue, and I'll talk more about revenue in a moment, as a quadratic function r, so r stands for revenue, in terms of n, where n is the price increase from $8. So when you raise it by $1, n is 1. Raise it by $2, n is 2. Take away money from the cost, lower it, n is a negative number. And we want to write this function in vertex form. All right, so first, what is revenue again? Revenue is not profit. Revenue is a fairly simple idea. Revenue is just all the money that comes in. Profit is much more complex, because you have to take away all the costs. But revenue is the same as just the price per item, which is currently $8, times the number of items sold, which is currently about 100 a week. OK, so let's write this as a function. So let's write r as a function of n. That's what we kind of want here. That's what it literally says up above. I want r as a function of n, where the price per item, again, it's yes, right now it's $8, but it can change. So it's 8 plus whatever n is, n being the price increase. And even if we want to look at the idea of lowering the price, we can still use this. And it'll just be a negative number. So again, $8 is the price right now, but it can change. So 8 plus n represents the price per item, knowing that n again is the change in price from $8. And the number of items sold, right now it's 100. But every time we raise the price by $1, we lose 2 sales. That's the prediction. So right now it's 100, but we lose 2 sales for every time we raise the price. And again, being the price increase from $8, as is highlighted up in yellow up there. What I just did there is, I think, the hardest part of the question. And hence we have an example like this. Now we have a quadratic function that's kind of in a factored form right now. But I said I wanted to write it in vertex form. So how do we write it in vertex form? Well, let's first FOIL this all out. 8 times 100, 8 times negative 2n, n times 100, and n times negative 2n. Now you can see how we have the makings of a quadratic equation again. I'm going to put it in standard form. So I'm going to write the negative 2n squared first, combine those like terms with n. I get positive 84n, and put my 800, the constant, last. So now it's written in standard form. In fact, let me label that. OK, I want it in vertex form. Well, how do we put it in vertex form? We complete the square. And so that negative 2, I want to factor out from just the first 2 terms. If I take out a factor of negative 2 from 84, it becomes negative 42. Give myself some space, put the 800 over here. I want to create my perfect square right here. So half of 42, and then square it. Take half of 42, and then square it. You get 441. And so I need to balance this out, and this is where we got to be careful, because that 441 is actually being multiplied by negative 2. So that actually is negative 882. That's how I actually changed the function. I subtracted 882 in total, so I need to balance it out by adding 882 right here. And now I'm pretty much done writing this in vertex form. Negative 2, I have n minus 21 all squared plus 1,682. And this is in vertex form. So, OK, I answered the question. But this actually tells me a lot. Not only can I visualize this function, but it tells me a lot. So this leads into the next part. Sketch a graph of this function here, right? What I just have up here is r as a function of n. Revenue is a function of the n. And again, n represents the price increase from $8 from the current price. So let's sketch this and then think about what this sketch represents. OK, so again, I'll just write the function up here, r of n. And I'll write it in vertex form. OK, so what do I have here? Well, in this case, instead of x and y, I have an n-axis and an r-axis. R being the revenue, n being the price increase from $8. I can see I have a quadratic function with a vertex at 21, 1,682. So all I really care is it's somewhere in this first quadrant. I mean, I don't have to set up, I can set the scales up any way I want. So I'll call it right here. I'll say this is 21, 1,682. There's my vertex. I know it's opening down. I also know if I look back at in standard form, I can see right here that's my y-intercept, 800. So why don't I label that right now? I know this, or I should say my r-intercept, I guess. So I don't know. Let's say 800 is about here. And I know all parabolas are symmetrical, so I know this has got to look something like this. Actually, yeah, that's good. I'll go with that. And then goes back down. OK, that's my kind of lousy, but good enough sketch of this revenue function. So what does this vertex represent? Because this vertex represents something really important in this scenario. What does that 21, 1,682 represent? Well, that's the highest point of my revenue curve, which means this represents the highest possible revenue. which is in a business probably what you're trying to maximize, probably. This represents the greatest possible revenue according to our model, right? This is all based on a prediction. And that revenue is $1,682 per week, because it says this is all per, everything was per week. But what does a 21 mean? This means when n is 21, but n is a price increase, so when the price is increased by $21. That's a pretty big increase. Not when the price of each bottle is $21, when it's increased by $21. So that means each bottle is $29. So according to our model, if we want to maximize revenue, we should raise the price from $8 to $29. We'll sell a lot less, but make considerably more money, because this 800 right here, that y-intercept, that represents when n is 0, which means when we don't change the price. That represents the amount of revenue we're making right now per week, $800 a week. And so compared to that, this is more than double. And so again, according to the model, this is a, we should raise the price significantly. And it makes sense. As we raise the price, we sell less, but we make more. At some point, though, you raise the price too much, you just get less and less people buying it until eventually no one buys it anymore. And if I were to look at if I were to continue this graph and find the x-intercepts here and here, these would represent when either the price is so low that we just don't make money anymore. And notice this, for example, if we were to work this out, this is at -8. And in fact, am I actually asking you to figure that out? I am. And so that said, maybe I shouldn't have told you that just yet. In fact, that's at -8 and this is at 50. Those are my x-intercepts. So how do we know that? Well, that's where my revenue is 0. Those are my x-intercepts. I can figure those out quite nicely, quite easily, if I look back to my equation right here. If I look at my equation in this form, I can actually see those values quite nicely. And so let me talk about that. Let me write down that equation in, not vertex form, in factored form. The 8 plus n and the 100 minus 2n. If I look at that form of the equation, if I make this equal 0, that'll tell me when the revenue is 0. And that's what this line here, this line represents when revenue is 0. And we can solve this by looking what we've done actually several times in this course, by looking at a quadratic equation and inspecting the factors. I can see right here when n equals -8, that factor will equal 0, and therefore the whole equation will equal 0. And I can see right here when n equals 50, because 100 minus 2 times 50 is 100, or 0 actually. And so when n equals 50, that factor will become 0. And so I know that when n is -8 and when n is 0, this whole equation, the revenue will equal 0. And that's how I know these two x-intercepts, or n-intercepts, if you look at the graph. And so in this case, that -8 represents when we take away $8 from the price. Don't forget the price was $8. So that means the bottle's now free. Yeah, you'll give away a lot of them, but you'll have no revenue. And this represents we raise the price by $50. So each bottle costs $58. And according to our model at that point, no one will buy it anymore. And so what's the domain and range of this function? Well, this function, while I can continue the parabola this way, it doesn't make sense anymore. The context doesn't make sense. In this case, you're giving away the bottle. But again, that doesn't really make sense in this context. In this case, you're charging so much, you're making negative money. That definitely doesn't make sense. And so this model, which predicts how revenue will change based on the change in price, is only useful when the domain is when n is between -8 and 50. And so I'll write that down first. So the domain is from -8 for n up to 50. And again, I put n instead of x because there is no x in my function. There's an n. And the range is at the very highest 1,682, at the very lowest 0. Because again, this graph stops the x-axis. And so again, by thinking about the context of the question, that we realize how that affects the domain and range. Again, this model here, and again, it is a model. It's all based on a prediction that every time you raise the price by $1, you sell 2 less a week. Based on that prediction, if that prediction is quite accurate, this is a very good model, but it's only useful between, this idea of bringing it down to 0 price or up to $58 if you raise it by $50. After that, this model is meaningless. All right, so let's look at a final problem. Again, an applied problem, but a very, very different one. So I say a rectangle has a perimeter of 20 centimeters. Express the sides of this rectangle in terms of x. Well, perimeter is a distance all the way around. So here, all the way around is 20 centimeters. Good thing about a rectangle is, this distance right here is identical to the other half. So everything here that is highlighted in green must have a length of 10 centimeters total, the part that's highlighted in green. Which means if I call, let's say, this side right here x, and this must be the same, then this side at the bottom is going to be 10 minus x. Because together, everything that's highlighted in green must equal 10. So if x is 2, then the longer side is 8, 10 minus 2. If x is 5, the other side is 5, and so on. And so I've now expressed every side in terms of x. The top is 10 minus x. The bottom is 10 minus x. The left and right are both x. All right, first step done. Model the area as a function a of x. So area as a function of x. So area of a rectangle is just length times width, base times height, however you want to think about it. In this case, x times 10 minus x. So area as a function of x is, I'll put the x first. Doesn't really matter, x times 10 minus x. And I'm done. Although, I can write this in different forms. And so, right now, this is in factored form, which in the last question was really useful for finding the x-intercepts. If I distribute the x, I get 10x minus x squared. If I write this in this order, negative x squared plus 10x, now it's in standard form. Notice in standard form, there is no constant term because it's a 0. And if I complete the square, I can put it into vertex form. And if I complete the square, the first thing I do is factor out the negative. So I have x squared minus 10x. Give myself some space. Again, there's no constant term to shove off to the side. If I want to make that a perfect square, I have to take negative 10, chop it in half, get negative 5, and then square it. So I get positive 25. So I have to balance that out by adding 25. And again, because this positive 25 is being multiplied by negative 1. So really, I subtracted 25 right there. So to balance it out, I have to add 25. And so I have a factor of x minus 5 squared plus 25. And now we have is, again, in vertex form. All of these three forms I've labeled here. The factored form, standard form, vertex form. They all have different uses. And lately, we've been dealing definitely mostly with vertex form. So lastly, let's sketch this function and state again what the vertex represents, and state the domain and range and all that. And so I have this set up already. Again, I have an area on the y-axis and x on the x-axis. X representing the length of that shortest side. What do we know? Let me write down the equation. The equation in vertex form, which is most useful for sketching this out, was this. So I can see the vertex is at 5, 25. I'll just put that, call it here. I can see it's opening down because there's a negative in the front, but there's no stretch. So I know it's opening down. That said, I want to also sketch the x-intercepts now that it looked at something similar in the last question. If I look right here, I can see the x-intercepts really quickly. If I just imagine this equaling 0, which means the area equals 0, which is what the x-axis is in this case, I can see one of my solutions must be where x equals 0, and the other solution must be where x equals 10. So I know when x equals 0, the output is 0. When x equals 10, the output is 0. Which which means this has x-intercepts at 0 and 10. So 0 is exactly right there, 10 is right here, I'll say, and now I can sketch this with a good degree of accuracy. And like before, this function doesn't actually make sense if I continue it below the x-axis, because the y-axis represents area. So this region here represents having a negative area, and x more than 10, or x that's negative as well. None of that actually makes sense. So my function is just this dark part of the parabola I've sketched out, which means the domain and range I can now state right now. The domain is only from 0 to 10, not all real numbers, because again, this model does not make any sense as soon as x is negative or as soon as x is more than 10. If you look back to my image here, this is what everything's based on. How on earth could x be negative, and how can x be more than 10? If x was 11, then that means this side here would be negative 1 in length. Again, that's not possible. And because the domain is not all real numbers, the range is not, just everything less than 25. The range is all the possible areas, and the range in this case is from 0, which is the least possible area, to 25. That's the most possible area. And this vertex here, this represents the greatest possible area. Of this rectangle, of a rectangle with a perimeter of 20 centimeters. That was the original setup. In this case, the greatest possible area you can have if a rectangle has a perimeter of 20 centimeters is, the area is 25 square centimeters when x equals 5. And if x equals 5, if I look back to my diagram here, if this equals 5, then this equals 5, which means we have a square. See the square of side length 5 centimeters. So the square is the most efficient use of the perimeter. It gives us the greatest possible area. And now I know that from looking at this. All right. As with a lot of these last lessons, fair amount of time that goes into these. And compared to the work we did earlier on in the course in the first couple of units, there's not nearly as much algebraic work. There's some, but not as much as we had in some of those radical questions and polynomial functions. But doesn't mean this is easy. Really, really important ideas here, though. So these ideas we'll continue to build on in the remainder of this unit and future courses.